Hey everyone, welcome back, and today let's solve Leetcode problem 166 titled Fraction to Recurring Decimal. So not very long of a problem statement here, but just to make it even more concise, basically we're trying to convert a fraction given as a numerator and a denominator in two separate inputs into its decimal representation and output that as a string, right? And the key kind of tricky part here is that we have to detect if there's a repeating cycle in the kind of decimal representation of that numerator over denominator fraction value and enclose those repeated cycles or cycle in a parentheses, right? So let's go ahead and look at the examples here. We see the numerator to be 1 in the example 1 and the denominator to be 2. That would mean we have 1 over 2 or 0.5. There aren't any repeating values. It's simply just 0.5 and it terminates there. For 1 over 3, for example, not one of the examples here, but 1 over 3 would be 0.333 repeating forever, and so it would be 0 and then parentheses 3. 4 over 333 is actually 0.012012012 repeating. The sequence of 0 and 2 that is what actually repeats, and so it'd be 0.0 and then 0 and 2 in the parentheses, right? And of course, for example, 2 over 1 is literally just 2. We don't even need a decimal, nothing repeats, we don't have a decimal value, it is simply just a nice clean whole number. So we're always guaranteed that we're not going to run into a division by zero error. The denominator is never going to be 0, which is great. We don't have to cover that like individual case there, and our numerator and denominators are actually going to be as large as and small and bounded as possible, of negative 2 to the 31st and 2 to the 31st minus 1, telling us that, okay, we have to have a pretty optimal solution in terms of runtime complexity. We can't have something like quadratic or exponential even, or even, like n times log n. It's going to have to be at worst linear, right? Or even better, logarithmic. Which brings us to how we actually solve this problem as a whole and the key observations that we really need to make to be able to solve this problem. And what is this key observation? Well, we're basically just simulating long division by hand, right? If you think about it, this really is a long division problem, and the only extra part is we're just looking at where the cycles are and putting them in parentheses, right? We're basically, when we actually do long division, and when we actually get a remainder that we've seen before, we know that that's actually where the cycle begins, right? So it's very similar in nature inherently to how long division works. It's just kind of putting that into code and how we actually put that and handle the logic for putting parentheses in those repeated cycles, which brings us to our main kind of solution approach to be able to solve this problem efficiently. So the first thing that we're going to do is actually handle our edge cases. We have to check for division by 0 or negative numbers. Now, I know that the problem tells us that we're not going to have division by 0. I'm just doing it for best practice, and more importantly, if we have negative numbers, because that's still a definite possibility. What if we're dividing by any negative values? And then once we handle those edge cases for any special inputs, then we have to actually calculate the integer portion. And that's very simple. We can just use Python and use integer division normally to just get our value of the numerator divided by the denominator for the fraction value. Once we get that value for that integer part division, we then have to actually simulate that long division for the decimal part. Right? We have to keep track of our remainders to check when we actually find a cycle. And when we actually detect cycles, basically when we actually see a remainder that we've seen before, we've actually found our repeating pattern, very similar to how it works in long division, and that's when we then enclose that pattern in parentheses. Right? Now, what is that key insight? Again, tying back to the main, really important insight and observation that we have to make to solve this problem, and that is, in long division, if we encounter the same remainder twice, we know that that pattern is going to repeat from that point onwards. And so when we see this kind of repeated pattern as we go through the decimal representation using integer division of the numerator over the denominator, that's when we know we have a pattern and we can enclose that pattern in parentheses. Which brings us to the actual solution. So again, I'm going to start off with something that's not actually necessary, but what I do for best practice here, the more simple edge case, and that is, what if we're dividing by 0? And it's a really good kind of best practice to have when you're dealing with math problems in general, or math heavy style data structure algorithm problems on Leetcode and other sites like this, or you're not sometimes guaranteed that you could or you're not guaranteed that the denominator is never going to be 0, right? So the first thing that we're going to do is, what if we do have a denominator by 0, division by 0 error? So meaning if denominator is equal to 0, immediately just return null or none, right? And the reason why is because, well, we can't divide by 0. It's quite literally impossible, right? So if this denominator here is equal to 0, just return none. We can't really do anything. Now, what is the next edge case here? The other kind of division by 0 or 0 division edge case. Well, what if the numerator is 0, right? If numerator is 0, let's use some simple math logic here. 0 divided by anything has to be 0 because you have to split 0 into some number of parts with 0 for each part, because you can't actually do anything with 0, right? If the numerator is 0, 0 over anything is always going to give us results of 0, regardless of what that denominator is, as long as it's not 0 itself. And so if this is the case, we always have to return 0 immediately, right? That's kind of the second edge case to handle. If we anytime if we have a numerator to be 0, we immediately return just 0. Now we have to actually build our resulting list, right? And I'm going to call it result. And this is what we actually output eventually. This is going to be our resulting list or string, and this is going to be initialized as an empty list here. Basically, it's actually to build our result, and the reason why we're using a list is because it's just really more efficient than string concatenation in Python. And so instead of combining strings, so using concatenation and the plus operator, we're simply just going to be appending values to the list. It's just more efficient in terms of complexity and readability in Python. Now, this is where that kind of appending operation, if you will, comes into play, right? So if the numerator is less than 0, and I'm going to put this in parentheses and you'll see why in a minute, if the numerator being less than 0 by this denominator being less than 0, using the XOR operator here, denominator, if I can spell, basically if XORed, if the denominator is less than 0, XORed by if the numerator is less than 0, we'd have to append to our result the minus sign. Now, why is this? Well, let's look at this. This is also another very important observation that we have to make. Well, basically, we have to use the XOR operator, which in Python is basically just this caret symbol, I believe is what it's called, to check if exactly one of the numbers is negative. If one of the numbers is negative, we know our result also has to be negative. And the way we can check this is if numerator is negative and denominator is positive, or numerator is positive and denominator is negative, we XOR that by checking if at least one of them, and or rather not at least, but if exactly one of them is negative and the other is positive, that means we have to have a negative kind of output there, right? The result has to be negative because a negative value divided by a positive value or a positive value divided by a negative value is always going to yield a negative result. And so we have to append a negative sign to our result. That's kind of the main observation that we have to make in terms of like signs for this problem. Now, once we take care of that, let's actually get our absolute value of our numerator and the denominator. Why is that? Well, because we've already handled the sign for what our output or result is going to be. It's going to be either negative or positive based on if these values initially were negative or positive, right? Once we handle that, once we actually get the accurate sign, we can just get the numerator and set them equal to their absolute value of themselves. So it's just easier to deal with them when we're actually dividing. So we're going to do the same thing for the denominator. Right? That's just really to help us because we've already handled the sign. An absolute value simply just converts these two values to positive numbers if they weren't already positive before. And I might have made a spelling error here. If I have, so be it. I'll handle that when we get the error while submitting the code. Now, this is where we have to actually calculate that integer part. We have to move on to that actual step of, well, what is the fraction value, right? And how do we get that? Well, it's literally just the numerator divided by the denominator. It's very simple. And then we have to append that value to our result. And so we're going to append to our result.append to our value, the numerator, you guessed it, over the denominator. And we're going to use something called integer division in Python here. So it's going to be 2 double slashes rather than just 1. It's also called floor division here, and it's going to be over the denominator. And then I'm going to take the string of this representation, right? Because that's the form that I want to have it in the actual resulting list that we convert back to a string, right? Basically, we're just calculating the integer part or the integer result for the division using the floor division operator, which is these 2 slashes of the numerator divided by the denominator, and then we're converting it to a string and adding that corresponding resulting value to our result, right? Very straightforward. Once we do that, then we have to actually get the remainder after the integer division to help detect those cycles and to use that for our actual decimal portion of our string output. And the way we can handle modulus in Python is simply just get numerator and mod it equal to the denominator. So now, numerator is going to be set to the remainder after the integer division, right? Just to make sure I spelled this right, numerator, denominator, perfect. Right, perfect. So now, our remainder of the numerator over the denominator is actually stored in our numerator itself. So if this numerator keep in mind this is now actually our remainder keyword is actually equal to 0, we immediately have to just return whatever our result is, because we know if the numerator is equal to 0, since numerator is now equal to the remainder, that means the remainder is also 0. If there is no remainder, meaning the remainder is 0, we have a clean division whole number. We don't actually need any decimal part. And a good example of this is example 2. We had the numerator to be 2, the denominator to be 1. 2 over 1 is 2. We don't actually have a remainder, and that means we don't need a decimal value or any decimal itself, and so we simply just return the result of 2 over 1 or just 2, right? That's very clean whole number results. But what if we do actually have a remainder? Well, if that's the case and we haven't actually entered this if loop here, or this if conditional, then we do have a remainder. And so if we do have a remainder, we're then going to append it to our result the remainder sign, or rather the decimal sign, because we have to actually have a decimal point for whatever our remainder is. And now we have to actually get our positions and each remainder based on where it actually first was positioned in our decimal part to actually check for cycle detections. So I'm going to call it remainder map here. And it's going to be initialized to an empty hash map. What is the whole point of this hash map? Again, this is really important. This is to store each remainder and the position where we first saw it in our decimal portion to actually detect for different cycles as we form different patterns in the remainder representation of our fraction numerator over the denominator value. Now, once we get that numerator, now we can start our main while loop here. So while our numerator is kind of valid, meaning while it's not equal to 0. So while this numerator is actually, kind of processable, if you will, meaning we have to continue long division until either the remainder becomes 0, meaning it's a terminating decimal, or we actually find a cycle. Because keep in mind, numerator at this point is equal to our remainder. So while the remainder is not equal to 0, which means if it is equal to 0, we have the terminating decimal, or while we don't find a cycle here, we're going to first check, okay, is the current numerator that we're currently working with, is it in the remainder map? Again, recall what the remainder map is. It's basically just to store those different remainders where we first saw them with their corresponding position. So if the numerator is in the remainder map, what does that mean? Well, that ties back to that main key observation. If we've seen this remainder before, like we see in long division, we've found the start of our repeating cycle. If we found the start of our repeating cycle, this is where we start implementing the parentheses logic. And so if that's the case, we get our index to be remainder map at this numerator. That's why this remainder map is so important. We get the position of where it first occurred for this repeating pattern, and then we append, or rather insert to the result, so result.insert at that index for our first parameter, and our second parameter, you guessed it, is going to be the open parentheses, because now at this index where this pattern that we just saw repeated first, we have to first append this opening parentheses and then the closing parentheses after. So result.append the closing parentheses after that, and finally just break. Once we've handled that logic, right? We have to insert that opening parentheses at the position where the remainder first occurred, and then add a closing parentheses at the very end. Now, once we've done that, here, what if numerator wasn't in the remainder map? What if we haven't actually broke out from this while loop iteration? Well, if that's the case, well then we have to actually record this remainder and its current position, and then use it for future cycle detection. And the way we would handle that is first setting it in the remainder map, so remainder map at this specific numerator, or remainder, if you will, has to now be equal to the length of our result, because that's its position. It's basically the number of characters that we've seen so far. That's also equal to the index, because it's the current one that we're currently processing right before we actually append it to its index. It's going to be its current position, which is just the number of characters that we have so far right before this specific numerator, or remainder. Once we do that, we then have to actually multiply the numerator by 10. So times equals 10, and keep in mind the numerator is just the remainder. Now, we then append to our result. Forgot the string. The string representation of, again, you guessed it, numerator over denominator. This is the updating part of our numerator, and we keep doing this until it actually becomes 0, or until we actually break and find a cycle. So numerator over denominator. And finally, the final step that we have to do, we then set numerator to be updated by modding it by the denominator once again. And we keep doing this until it actually hits 0, or we find a cycle. Now, what you guys just saw here, apart from line 24, but from lines 25 to 27, is the key part of long division. We're multiplying the remainder by 10. That's basically the same thing as adding a 0, and then dividing by the denominator to actually get the next digit, and then updating our remainder accordingly. This is the exact same process we follow when actually doing long division. We're just converting that into code with the different input parameters that we're actually given. And finally, once this while loop is done executing, once it fully terminates, we then have to actually join all of our parts into a single string from the resulting list and just output that accordingly. So not only would we just return the result, we'd return the string representation of the result, which would be string.join of our result. We're simply just joining all the elements in this list here into one singular entire string and returning that as our output. So unless I made it in syntax 0, 0, there should be accepted and there should be a valid solution. So let's go ahead and verify that. Okay, let's go ahead and see what I did wrong here. Okay, so clearly I just completely forgot to put result. Very dumb mistakes like this happen, guys. Sorry about that, but now this should be accepted, and now there should be a valid solution here. And as you can see, this really is just about as efficient as you can get it to be. So again, on a high level, how are we really solving this problem as a whole? Effectively, we're simply just simulating, again, the key portion, long division process. This is what we learned in probably like middle school or elementary school. I don't know when different countries teach it. But the main insight here is when we're actually simulating this long division process, we're simply just actually encountering the same remainder twice, right? And if that's the case, if we encounter the same remainder twice, that's when we know we have a cycle, and all those subsequent digits in that cycle would repeat in the same exact pattern, and that's why we put parentheses at them of where they actually first appeared, right? To avoid any duplicate parentheses, and that's what we kind of handle when performing long division. So how does the algorithm work as a whole? Effectively, we first pre-process our inputs by handling the signs and those different edge cases like we saw at the beginning. Then we actually get the whole number representation or the decimal representation using integer division in Python. Then we actually simulate the decimals by performing long division digit by digit, and then actually checking for different cycles. We use our remainder map to identify when we actually find different patterns that repeat as we iterate through the different patterns potentially in the decimal representation of our fraction value of the numerator over the denominator, right? That is the main kind of observation. The key breakthrough here is that we have to actually realize that the remainders are nothing but the state of our division process, where the same remainders mean that the same future behavior is going to happen, right? Which brings us to the complexity of the solution to wrap this video up. Effectively, like we talked about at the very beginning of this video, we had to have efficient solutions because of how tight our input constraints were. They're very large. And so for our runtime complexity, this is indeed linear. It is big O of D. D is going to be the number of digits in the decimal representation. And the reason why is because in the worst case, we have to actually potentially process every single possible remainder before actually finding that first cycle. And since we know our remainders are bounded by the denominator value, we would have actually at most a denominator 1 unique remainders before we actually find the cycle, right? And that's the reason why it's going to be really just roughly big O of D. Because worst case, if we find that denominator or cycle at the very end, and we know that our remainders are bounded by the denominator value, we'd have at most denominator minus 1 unique remainders. Which brings us to our memory complexity, or our space complexity, if you will, also big O of D for, well, honestly, the very same reason, just in terms of data structures. Because the reason why, because we're storing each remainder in our hash map here in the remainder map hash map. And so we're building our resulting string as well. And both of those data structures are also bounded again by the number of decimal digits that we actually generate, which is also bounded by that denominator value. And finally, the last final observation that we have to make, the maximum number of digits before a cycle is actually just the denominator minus 1. The reason why is because there are only denominator minus 1 possible non-zero remainders, and that's why that math kind of checks out like that. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in my next video. Bye-bye.